Okay, so yeah, we were looking at this
Straight line diagram, yeah.
straight line children's drawing and
Trying to get some sort of polynomial from it, which you're suggesting might be related to a Shabat polynomial, whatever a Shabat polynomial.
yeah, I had the vague impression that Shabat polynomial has something to do with any one that you of these polynomials that you get from a tree.
Well, yeah, I mean, it's pretty much these trees that give polynomials. The other ones will give more complicated sorts of
yeah. And then
projections. Yes.
Yeah, and these straight line ones supposedly give Chebyshev polynomials, which are famous as orthogonal polynomials on the interval or something like that. I can't remember what characterizes them, but they show up as orthogonal polynomials.
Yeah, well, let me say some very lowbrow stuff about those Chebyshev polynomials, but let me just go to a new page here. Where's the thing? I mean, I guess the example that we were starting to work out last time was the tree that was really just, no side branches at all, just a straight line. I think it was this length, so it'd be a cubic. So this would be according to whatever rumor you ran into, this would be the cubic Chebyshev polynomial. And well, so let me try to well, look, so since it's a straight line, we're sort of expecting you can sort of see all the characteristics of this polynomial function by actually graphing it as a real function. And perhaps that's the way you might typically visualize a Chebyshev polynomial. I'm trying to remember. So, okay, Chebyshev polynomial, is that one of the ones? I guess you're telling me that is one of the ones that shows up in basic quantum mechanics. But is there a more famous one that shows up in quantum mechanics? Let's see, there's the Laguerre polynomials.
Laguerre and Legendre polynomials show up.
Maybe that's what I'm thinking of. But Chebyshev, okay. So let me try to draw a very sketchy sketch of what I'm expecting this to look like qualitatively. So it's I mean it's got these, what am I trying to say? I mean, the greens in my picture are where the polynomial is reaching the value 0, and the reds are where it's reaching the value 1. Is that right? I guess I've got it reversed from left to right because I want to look at it this way. I want to say, so, okay, this is my, what do you call it? The x-axis or something like that. That's where, so I'm going to think something like this. A cubic polynomial that looks like that. So this is supposed to be, y equals 0, and this is y equals 1.
Mm-hmm.
And so the next one would be like this. And so it would end up looking like what? It would end up looking like let's see, it's hitting 0 over here, and then it's hitting 1 up there, and it's coming back down to 0, and it's going back up to 1. It's going back down like that. So it's evidently that's what this quartic Chebyshev polynomial should look like. By the way, let me just, as a random side comment, let me mention that this vaguely reminds me of stuff that I remember reading about Vladimir Arnold talking about, where he would like study the sort of profiles of polynomials or functions like this or something like that, where you keep track of in what order the local maximums show up or something like that. And a long time since I read this, he related to like Young diagrams, might have been related to Vasiliev polynomials or something like that. But I have a feeling these examples might have showed up as sort of like, right? These are like ambiguous points, points that like need to be resolved in this. You know what I mean? Because like,
yeah, because you're
getting a whole bunch of ties between local maximums and local minimums and stuff like that. So yeah, I just wanted to mention that I have some vague memories of reading Vladimir Arnold talking about stuff like this, that I don't remember the details that we were talking about it, but could be interestingly related to this. But
it reminds me of Rene Thom or someone saying that the constant function is like the most complicated function, because in any neighborhood of it, there's like infinite.
Sure, that's different. Yeah, that's interesting. That's interesting. Yeah, I mean, it's the most special.
Yeah.
So perhaps the last silly comment I wanted to make about these things was that, it's sort of visually obvious that, for example, this one's going to be even and this one's going to be odd if you calibrate them the right way. So the actual system of equations that we were working with last time, the actual system of equations, it turned out to be, it didn't look like an odd polynomial last time, but that was just because we had, I think my 0 was calibrated to be over here. And right, we had the system.
One you wrote down last time, it was a cubic polynomial. Maybe you later realized.
Yes,
something.
no, there was a. Am I saying this right?
Oh, odd in the sense of, sorry, you meant odd. Okay.
Yes, that's what I meant. Yes.
Yeah.
Yes. But wait, okay, but you're going to be mixed up already. So the cubic so let's see, we had right. I mean, right. We had.
In my notes, I have the names of those dots, 4 dots being L10M is what we did.
Really? Okay,
Yeah.
I'll do it that way.
I mean,
I was gonna label it differently, but L10M. You
may have had a different red green convention. I just have black and white in my notes.
Sure. I'll pretty much have to be pretty sloppy about that for now. Pretty careless about that. So I think I was, calibrating it so that 0 would go to 0. And 1 would go to 1, which would kind of put, right? I mean, that would kind of put, 1/2 would be somewhere in the middle or something. That would probably be, right? That's why I wasn't getting an odd cubic polynomial, because I didn't have it calibrated so that, I should have it calibrated in order to get the odd polynomial. I should have it calibrated so that 0 is right at the origin, at that midpoint.
I see.
And same for this next straight line one, which is the quartic one, which is an even polynomial, but only if you calibrate it. Well, that one probably would come out automatically if I put 0 there.
Yeah. I guess. Yeah.
So yeah, right. So as usual, it's okay if you're cheating, but I'm mostly not cheating. I really should cheat more. Maybe you should cheat less, but maybe it balances out.
Well, all I really absorbed from that was the name Shabat and Chebyshev. I didn't have time to exploit that.
Sure. And yeah, I mean, right. But so at this point, what we were doing is we're kind of trying to derive a system of equations for the coefficients of this Shabat polynomial. In this case, the coefficients of this cubic Shabat polynomial with auxiliary variables given by this L and the M. So, by the vertexes of the diagram.
By the way, in your picture, does it come out to work out nice if you take M to be less than 0 and L to be bigger than 1, so that the line of dots is like the line of points on the x-axis? I mean, I guess L and M can be anything, right? Or is that so they don't have to be linearly ordered. But anyway, I guess they can be anything, right? So
yeah, I mean, see, I really did, when I worked this out, I had this slightly differently calibrated. I'm a little surprised. So you really think I did have like one there?
Well, you can look back on your notes and check. I don't know how hard it is. Maybe it's a nuisance.
Yeah, I mean, I remember having it at one point. I had it calibrated slightly differently. I had it calibrated. I'm gonna, be really sloppy here and calibrate it a little bit differently. Let's see. Yeah, I think the way I had it was, I actually, right. Okay. I should. I think I had it like calibrated. I had it set up so this was 0 and this was 1. So it was even more disorganized. I had it this way. And when I worked it out this way, it came out to be like 1, 0, and -2 and -3. Right, that one.
Oh, so I was completely wrong. So you can't get L and M to be whatever you want. Okay. Okay.
What do you mean you can't? What do you mean? Yes, you can get L and M to be whatever you want. I mean, you have the triple transitivity. That's the amount of freedom you have.
Yeah.
So that means
so
2 is less than 3. So you can get any 2 to be anything you want. Yeah. So you could make the 2 endpoints be, something negative on the left and something positive on the right. Maybe I didn't understand what you were asking for or what you were saying.
Yeah, well, I'm getting more confused. But haven't you eaten up some of your triple transitivity by picking 1 and 0 to be 1 and 0?
Yes, and in fact, by having it be a polynomial, this Shabat polynomial, we've also nailed down infinity. So yes, as soon as you but I was utilizing that freedom at some point. Remember originally we had you were suggesting at one point that I had the L over here and the 1 over there. And then in that case, I would probably be getting, 1 there. And I guess this would be -1/2 and this would be +1/2.
I have no idea.
I mean, I'm just right before I had like, it was this gap in the middle was 2 and the other gaps were 1. So now that I've recalibrated it so that the gap in the middle is 1, that means that these other short gaps should be 1/2.
Okay.
Isn't that okay?
Yeah, I guess. I'm confused, but yeah.
Anyway, at this point, we're just fooling around. We're not doing anything systematic yet. I should really get to more systematic wild guesses instead of just very unsystematic wild guesses. So yeah, right. Let me try to organize my thinking here a little bit more clearly. But let's repeat what we're doing here. So we're sort of aiming to construct this polynomial from the child's drawing. And we're suspecting that this is called the Shabat polynomial. Well, from this tree, this special tree case of a child's drawing, we're aiming to construct a particular polynomial, which we're now suspecting this is called the Shabat polynomial of that tree. And yes, if you calibrate things correctly, it's precisely defined. But the way that we have so far for trying to construct this involves trying to write down a bunch of sensible algebraic equations, a sensible system of algebraic equations, where the variables are the coefficients of this Shabat polynomial plus the locations of the critical values, or maybe I should say the locations of the zeros and the ones of the polynomial, the zero values and the one values of the polynomial. And so we're writing down that system of equations, and the system of equations doesn't just have a single solution all the time. And which is sort of a bug and a feature. I mean, this is how the Grothendieck Teichmüller action ended here. I mean, what am I trying to say here? I mean, one way to think about what we're doing here is that we're trying to create this functor that takes as input a child's drawing, perhaps especially in the tree case, and gives as output a system of equations over the rational numbers, which you could think of as an affine algebraic variety over the rational numbers. And in fact, it'll be a zero-dimensional affine algebraic variety over the rational numbers. And simply by virtue of accomplishing that, you're obtaining something that is acted on by the absolute Galois group of the rationals, right? Because I mean, the solutions of this system will be acted on by the absolute Galois group. The solutions over the the solutions over the algebraic closure will be acted on. So you see what I'm saying? In a very conceptual, automatic way, functorial way, we're getting, we should be getting an action of the absolute Galois group. So that's a good thing here. But on the other hand, so far this system of equations that we're getting, I mean, not only doesn't it narrow down to a single solution, which is good in a way because we're getting this whole Grothendieck Teichmüller multiplet, but so far we're actually getting a little bit more than that. We're not getting an irreducible polynomial yet. Let's see, is that right? So I guess the Shabat polynomial should be an irreducible polynomial. But what we're writing down so far is not an irreducible polynomial, or maybe I should say, at this point, we're not really writing down a single polynomial. I mean, we're writing down a whole system of polynomial equations, but you can still talk about, it being irreducible or non-irreducible. And so at this point, we're not getting the irreducible one yet, which means we we need to think of more stuff to write down, more equations to write down. Am I saying that right?
Can you start writing them down and convince me that it's not irreducible, or do whatever it takes to convince me it's not irreducible?
Yes, yes, okay. There's so many things to say here. I'm not saying them very well yet. Okay, right. At this point, we're still doing something very unsystematic. We're still doing examples. And we'll do this example. But I really have much more systematic functorial things to say. But okay, yeah, let's do this example. So, all right, so I've got a lot of crossing out there. Let me just try to really let me just clean that up. So okay, and I think, you know, I'm just going to use what I remember using the last time I solved this system. So it was like 1 and 0, and I guess we call it L and M, I guess, like that. So I guess there is a danger that we're writing down a slightly different, you know, the system equations will look differently because I may have rearranged the variables here, but I think that'll be okay. So we're trying to, so we're going to have this, we're aiming for a Shabat polynomial that will be of the form, you know, f of z equals g z cubed plus h z squared plus j z plus k.
Okay.
We're aiming for that, but you know, but that means these coefficients are among our variables, and the L and the M are also among the variables. So that means we have these 6 variables: G, H, J, K, L, and M. And then we need to write down our 6 equations, and we're just going to, you know, roughly balance out our 6 variables. Hopefully that's going to happen very typically, like maybe all the time. And in this particular example, the way the 6 are spread out is sort of like there's 1 equation over here, 2 over here, 2 over here, and 1 over here, which you can think of as corresponding to the number of edges coming out of the vertex. Right, because we're saying that, you know, we know the value up to what?
Oh yeah, I get it.
Yeah. So we know the value up to 0, up to, how do I count it? Up to 0th order at these endpoints, but at the middle points we know the value up to, we know the function up to 1st order at those critical points. So let's try to write them down. So what are the 6 equations? I mean, they're f. Don't tell me. Let me think. Okay, so right, there's 1 for f1. There's 2 for, there's 1 for f of 0 and for f prime of 0. Sorry. And there's 1 for f prime, and there's 1 for f of L, 1 for f prime of L, and there's 1 for f of M. So let's see. F of 1 should be 1, f of 0 should be 0. F prime of 0 should also be 0. F of L should be, is it 1? Yes.
Yep.
F prime of L should be 0. And f of M should be 0. So it's these 6 equations. And let's try to grind out the system from this, okay? Because it's not that bad. I have done this one. This one's not that bad. We can just fumble our way through it. So what am I trying to say here? That, oh, well, so like, for example, this one is very simple.
Right. I was going to say.
Yeah, that's basically just telling us that's going to eliminate K for us. Is that right?
Yep. So that's good.
Yes. So we're now down to 5 variables and 5 equations. And this next one is working in a very similar way. That's just going to eliminate J for us.
Yep.
Right. So we've now eliminated J and K. Because, you know, when you take the derivative of F and then evaluate at 0, the only thing you really see is J. So, yeah. Okay, so we're down to 4 equations in 4 variables.
I would do f of 1 equals 1 now myself.
Say that again. You did that one?
No, I would do that. That's
oh,
the next
okay.
one I would
Sure.
do.
Okay. So it sounds like you're saying, well, for one thing, it sounds like you're saying f of z equals g z cubed plus h z squared.
Yep.
Which again doesn't look like an odd polynomial, doesn't look like an odd cubic, but that's just because we didn't have it calibrated with so that 0 was in the middle. Right, but it is qualitatively an odd polynomial if you calibrate it that way. Right, we already mentioned that. Okay, so
so g plus h is 1.
G plus h is 1. Okay, that's, yes, that is very helpful. So
And then we get to the more annoying ones.
sure, but which ones should we eliminate here? I mean, should we eliminate G or H? Is that going to make a huge difference? Let's see. Okay, let's write down what these last 3 at the bottom look like at least. So what do they look like? They look like G. Well, okay. Maybe I don't know. There's probably all sorts of elegant ways to do it, but let's just, yeah, let's just try to
See what we got.
yeah, let's actually eliminate H from this from this equation here. So we've got f of z equals gz cubed plus 1 minus h. No, 1 minus g z squared. Is that right? Which is equal to what? G. I mean, it's equal to itself, but plus z squared minus gz squared, something like that.
Okay, does that help? Okay.
Well, I mean, you could take the lead here if you want.
Okay, whatever. No, anyway, fine. I would not factor it out, but anyway, we're gonna stick L in there.
Yeah. I'm just fumbling around here, but I would be perfectly happy if you take over and do this. I guess it's hard for you since you don't have the screen or control.
I can talk. I can say what.
Okay, I'll try to do that. Go ahead. Okay. But should I just write these out here?
Yeah, I was just gonna be basically starting by writing those out.
Okay, expanding those. Yeah.
So I'll do it, but I will not expand that 1 minus g thing out.
Okay, so
I don't yet see why I want to do that. So, okay, so I get
g times L.
G L cubed.
Yeah.
Plus 1 minus g L squared equals 1.
Equals 1. Okay.
And then I want to do the M1 next. So gm cubed.
Okay.
Plus 1 minus g m squared.
Yeah.
Equals 0.
Equals 0. Yeah.
Sorry, I'm just thinking for a minute about what I would
Sure.
do with that next one. Like that one there is interesting because, just digressing slightly, that one would be solved by m equals 0, but it would also be solved by something else. That is, if you assume m's not 0, then you get another thing.
Right, and that's interesting that you brought that up. I mean, again, I don't completely understand what's going on here, but if you look at our diagram, what am I trying to say? Oh, by m equals
so maybe
right. I think we don't want m to be 0. We don't, right? That would have the two green points collide. We don't want. So somehow that's something we've got to factor out.
Yeah.
Eventually, but we don't have to worry about that yet, unless you have some clever way to factor it out right now. Maybe
Well,
you do.
I mean.
Okay. So it sounds like now you're saying GM plus GM equals what? G minus 1.
Yeah.
So this is more elegant than however I did it. So GM equals G minus 1.
Mm-hmm.
And so you're saying that you've got a solution for M. All right. Boy, I really don't remember getting exactly this way of thinking about it. G minus 1 over G.
Mm-hmm. Okay, yeah. So anyway, the third one, which I was saving for last because it's the most
Yes.
Well, it's not that unpleasant. So let's see. I'm going to differentiate f, and I'm going to stick 0. Wait, I'm going to stick L in it.
Yes.
So I'm going to get 3GL squared plus 2HL.
Should I write down H as 1 minus G, or should
I? Sure, if you want to show off.
Well, no, I'm just trying to do it whichever way.
Yeah. Well, okay. Yeah, you should, since, well, so eventually we should, yes.
Times L
Times L equals 0.
equals 0. Okay. Okay. Yeah.
And then again,
yes,
we don't want L to be 0.
Right.
So you
Agreed.
can factor out that L. And this is actually letting us solve
3GL plus 3GL equals what?
You can say equals 2G minus 1.
2 times G minus 1. Okay. Okay, so now what does that come out to? You're solving for L? You're suggesting solving for L, is that right?
I guess I was, yeah. I don't know what I was quite gotten that far. That's good. Yeah, it's very good to solve for L. So L is 2/3 G minus 1 over G.
Which is actually M. Remember, we solved for M as G minus 1 over G.
Right.
So it sounds like you're saying it's 2/3 M.
That's nice. That probably.
Yeah, I think that fits with what I said before about my guesses for the.
This is something about them being like equally spaced in thirds of something like that.
Well, I mean, I said actually that that it works out in this case that they're not equally spaced. That for some strange reason in this Chebyshev polynomial, cubic Chebyshev polynomial, the gap between the two critical points is twice the smaller gaps to the left and right.
Okay. So let's see.
So that means I'm cheating here, but it's going to go 1, 0, -2, -3. That's the way it's going to go, and that exactly fits with what doesn't it? With the 2/3 thing here, that the L is 2/3. Yes, -2 is 2/3 of -3.
Oh, let's see. So, so what's the deal with G? That is, we don't know what G is.
Yeah, but we must have had, right? There must have been something that was gonna, right?
Solve for H in terms of G.
There must be an equation we're neglecting to exploit here because it's.
Oh, wait, let's see. Did we do f of 1 equals 1?
I thought we did. That was the one that.
What does that do? Oh, that was.
Oh, maybe we didn't. Let's see. Did we?
Oh, we did f of L equals 1. Wait, f of 1 equals 1. No, that gave us G plus H equals 1. Okay, so that's what.
Okay. Yes, you're right. Right. So.
What did we not do?
Was it the f of m equals 0?
No, we did that. That's what let us solve for m. That's how
What
we
about
got.
the f, then f of L equals 1? F of L equals 1? So that was
No, we wrote it down. That's the one that.
right here?
Oh yeah, but we didn't do anything with it. Okay, good.
Right, because it was too ugly to do anything with it.
Okay, at the time.
So do something with it.
Okay, hold on. Let me write it down again. I'm running off the page here with the scribbles of equations. So okay, let's see, what do we do now?
Yeah. This is like a big mess.
So we know so L and M are basically, we sort of know each. Okay, so yeah, this is where this is like the final punishing phase of the operation. So what we'll do is we'll write L in terms of M, but then we'll write M in terms of G. So in other words, we can solve for L in terms of G, or vice versa. Why don't we just write that down though? Those two.
Okay, so we're getting down to a single equation, a single variable, right? A single variable polynomial equation. Yeah. And what is that single variable polynomial? Well, what is that single variable? Did you decide? That's the big question. It's got to
L. I'm going to either use, well, we could either use L, M, or G. I think I want to use G.
Okay.
So I'm going to say L is 2/3 of M, which is 2/3 of G minus 1 over G. I'm using the bottom two equations, the ones near the bottom of the page. To say L is 2/3.
Yes.
G minus 1 over G.
2/3.
I really don't like this,
G
but
minus 1 over G. Yes.
So then I stick that formula for L into the equation in the box.
Yes. Yes. I was trying to get a little bit more room here. G times 8/27. Okay. 2/3 G minus 1 G. Actually, that 8/27, that could be very suggestive. But let's see. This thing cubed?
Yep.
Why is it so complicated?
I don't know.
I mean, that's coming out to like a, oh, no, okay, right. You got a fraction there. Okay. Maybe it'll somehow work out. Plus,
live with it for a second here. Plus 1 minus G times 2/3 G minus 1 over G.
Yeah.
Squared equals 1. Okay.
Equals 1. Okay. Can you grind that out? Do something with it?
So I'm just going to slowly simplify it. So we get 8/27 times G, the quantity G minus 1 cubed over G squared.
Yes.
plus, maybe I'll say minus
Minus.
4/9
Okay.
times G minus 1.
4/9 times a big thing in parentheses, or 4/9 times.
No, I'm doing it. 4/9
Okay.
times G minus 1 cubed on top over G squared on the bottom. That's good, right? Because that's the same stupid thing we saw before. Equals 1.
That's the whole thing, like that.
Oh, yeah. Because I got the 1 minus G and the G minus 1 squared on top. So that gives me like G minus G minus 1 cubed.
Okay, I'll try. That sounds plausible. I'll trust you.
Okay.
Equals 1. Okay.
So that's sort of nice, just because those disgusting quantities involving G are the same.
Yeah.
So I just need to know what 8/27 minus 4/9 is.
8/27 minus 12/27.
Yeah. 12/27.
So it sounds like you're saying negative 4/27. Let's see.
Negative 4/27. Yep, that's right.
Negative 4/27 times G minus 1 cubed over G squared equals 1.
Yep. So, well, you know, the different cosmetic things we can do here, mainly like multiply both sides by G squared to get a polynomial equation.
Yeah,
but
yes, let's just get a polynomial equation and then
declare that.
And then try to factor it or something like that.
Oh, sure. Okay. Oh boy. Okay. You're really
So.
Okay. So I'm just starting out by multiplying both sides by G squared. Oh God.
Okay.
I don't see it.
Yeah, see, I mean, somehow you managed to make the very start of this solution of equations, of the solution of this system of equations, very elegant, but somehow you paid for it by making the end of the process very ugly. Or I don't know, maybe I'm screwing up here somehow, but let's see. Multiply by G squared and you get.
I mean, usually if you make the start elegant, it helps be elegant.
Yeah, but it did something.
You usually don't say like, oh, I don't want to make it too simple at first because
I don't know why it's working out this way. Let's see. So this is
a very pessimistic attitude.
Negative 4 G minus 1 cubed equals 27 times G squared.
Yep. I mean, either we screwed up or we're just going to get what we get here, which. So, okay, I can cube that thing, but so can you, I imagine.
Okay.
I mean, I can.
It's like 1 minus 3G, no.
Yes, you're just cubing.
Yeah, yes. Okay. Plus 3G squared minus G cubed. So it's 4 times that minus 27G squared.
Yeah.
So it's
I'm trying to do it.
what? Yeah, this is really looking not quite familiar.
Uh-oh, we may have screwed up.
Yeah, I mean, I could easily could have copied something down wrong somewhere. Let's see. Can you find any mistakes in your notes or anything like that? Or what are we getting here?
Seemed pretty good. And for it seemed like
I mean, we pretty much had to come up with something cubic here. Is that right?
yeah, I think so.
Just confusing me here because
So what happened with you when you did it? Could you factor the cubic?
Yes.
Mm-hmm.
Yes.
Somehow you could see that you could factor the cubic.
The very elegant thing that you did, which I'm sort of blaming for causing all the problems, is the way you eliminated the degenerate solutions right up front.
Mhm.
Right, that thing where L is 0 or M is 0 or something like that. You somehow eliminated that. The way I did it, I didn't eliminate those up front, and I ended up with a cubic polynomial, and it had 3 linear factors that I could easily factorize it into.
So was it cubic? Oh, but
yeah,
was it just a polynomial in G, or did it have G and L and M?
I think it was in G.
How did you do that?
I don't know. I was kind of faking it, but let me see if I can remember what it was. Okay, I think it was something like, I think it was G, and I think it ended up being G cubed minus 3G plus 2. I think that's what I ended up with. Except it might have been, the signs might have been reversed from that or something like that. Does this one factor? I mean, what it was supposed to factor into? It was supposed to factor into G.
G minus 1 factors in there. It has a root at G equals 1.
G minus 1, G minus 1, and G plus 2. That's what I wound up with when I was doing it. And does that seem different from what we're getting here?
One thing you're making me think is that since like G minus 1 is so prevalent.
Oh, wait a minute. Except, wait a minute. Sorry, it wasn't the variable G that I had. It was the variable L that I had. Let me check the picture again. Where is L in the picture? Yes, L is that one that I'm expecting to work out to be -2. So what I actually had was somehow, let me cross that out. It was something like L cubed. Somehow I came up with L cubed minus 3L plus 2 equals 0. So I had L minus 1 and L minus 1 and L plus 2. And again, then at this point, you could, if just pretend for a moment that we got to this point. I don't remember exactly how I got to this point. I guess, right, maybe yours actually is correct, but maybe yours is written in terms of G, whereas mine was written in terms of L. And so, yeah, I can't even guarantee that yours doesn't factor. And but the point is that for L, if it factors like this, then this is the one that ends up giving the important thing. L equals -2. Because right, these other ones would say that L is equal to 1. And that's one of the things, right? That's another collision that we're trying to rule out in the
Right.
picture.
Right.
Where'd the picture go? I can't even see the picture here. It was up at the top. Yeah, it was, sorry. Let me cross this one out. Sorry. Getting a very messy picture.
Yeah, so anyway, at some point, I sort of arbitrarily decided to solve for L in terms of G.
That's right. Do you want to try to do that right now, or do you just want to trust me on
Well,
this? Or, yeah.
I'm getting a little worn out of this, but I was just saying that, like,
Yes.
I eliminated L in terms of G, but actually what you should have done right then is you said, like, no, L is more interesting to us.
I don't even know why L is more interesting to us. It's just that
Well,
when I worked it out, it did work out this way.
well, L is one of the positions of the dots in your child's drawing, whereas G is just some stupid coefficient of this cubic that, so if you're trying to find where the dots are, where the points are in your branch cover, then L is more interesting.
All right, I'll try. I'll think about that philosophy. That somehow the location of the vertexes is.
Yeah. So in other words, when I solved
More
for L
important.
as a function of G,
Yeah.
I could have solved equally well for G as a function of L, and maybe that would have been the wise thing to do.
Okay, so this was in fact intended to be a sort of an orgy of annoying calculation. And now let's try to adopt a different spirit and think more conceptually about what's going on here. Okay.
Mm-hmm.
So what am I trying to say now? So, right. Keep in mind, I'm attempting to be more conceptual now. So let me try to say more conceptual stuff, but that means I have to think, I have to fumble around in a different way. So what am I trying to say here? So, well, so let's pretend that we've sort of streamlined that calculation process that we just fumbled our way through, and pretend that we, have it streamlined to the point where we can do it for any one of these trees.
Mm-hmm. Okay.
And so if you think about it, the whole system of equations that we wrote down depended on remarkably little information about what the tree is. More specifically, the only thing it really depends on, if you think about it, is it depends on what I call the vertex censuses. So like, there's a census of the green vertexes. And so let's write down the census of the green vertexes and the census of the red vertexes in this example. So we had 2 green vertexes. I think one of them had, okay, so this is the color green, yeah. So the green gives us one with 2 edges. That's one we're calling 0. That's somewhere in the middle. And then one with just 1 edge coming out of it. So that's a full census of the green vertexes. And then a full census of the red vertexes is, I guess it was also 2 and 1 or something like that. And that's all we needed to calculate this system of equations.
Uh-huh. Wow.
So, right, and in a way that's a danger sign, right? Because it's saying we're not really exploiting a whole lot of information about the tree. We're just using these vertex censuses. So I thought about that a bit, and then I realized that what I'm calling vertex censuses is really something much more familiar. Should I say what it is?
Well, so it has something to do with we're imagining this branched cover, and we can like look at the points over 0 and 1.
Yes,
You can
that's
just like
right.
so there'll be like 2 points over 0 and 2 points over 1 in this case, and then you can go through those points and you can see, are they?
Did you say 2 points over 0 and 2 points over? Oh, I guess you're right. I'm sorry, you're correct. Yes, they're right. That's right.
Yeah.
For some reason, I was thinking 3. There's 3 over a generic point, but over
Right.
0 and over 1, there's just 2. Yes, that's right.
Yeah. And one of them is, I guess, I don't know if they call it a double point, but it's like a thing. It's that thing coming from the 2 in your picture there. That it's like
Yes.
looks like the Riemann surface of the square root function there.
Yes, yes.
And then there's one that's just like a normal a local diffeomorphism point.
Yes, yes.
So I mean, so that's what you get out of these.
So that's sort of your answer.
You sort of like look over 0 and 1 and look locally at what the branch cover looks like there.
Okay, but I want to say that in a somewhat crisper way. Should I just go ahead and say it the way I would like to say it?
Sure.
So, basically, I mean, you're describing this, permutation for rotation over 0, and this other permutation for, the permutation of the sheets over the branch point 0 versus the permutation of the sheets for rotation over the branch point 0, rotation at the branch point 0, versus the other one for rotation at the branch point 1. And it's, again, permutation of the same sheet. So these are 2 permutations on the same set. And it's a 3-element set. But each of the 2 permutations has 2 orbits, 2 cycles. And in both cases, it's a 2-element cycle and a 1-element cycle. So this vertex census for the green things, that's just the consciously class of the permutation.
Right. So can I, so
it's a Young diagram. Yes, go ahead. Yes. I'm sorry.
Each one is a Young diagram.
Each one is a Young diagram. Yes.
Yeah. So I was going to say that it's like there's something sort of something sort of double cosody or going on. So you have like
absolutely, yes.
So you have like pairs of permutations.
Yes.
Mod isomorphism class, a set with an isomorphism class of a pair of permutations. And so we've specified the data of each individual permutation, the isomorphism class of each one, and then there's like a kind of double coset-y thing about like the different ways you could fit them, they could interact with each other.
Yes, the orientation between the 2 permutations. That's right, the geometric orientation between the 2 permutations. And
that's nice.
So we're saying that this system of equations that we're getting, this 0-dimensional algebraic variety over the rationals that we're getting, is only depending on, this pair of Young diagrams, whereas the more detailed information is of exactly which child's drawing we're getting is depending on the orientation between those 2 things that, individually they're just classified by Young diagrams, but jointly there's this crucial orientation information between them. And so we're saying that we're getting this 0-dimensional algebraic variety, and it should have a whole bunch of different components that sort of course, I haven't gotten this to work cleanly yet, but roughly speaking, when we clean this up, it should be something like that the different components in this algebraic variety should correspond to these different orientations.
Huh.
And then the individual components should be irreducible over the rationals, but they should be reducible over the, in general, they should be reducible over the algebraic closure of the rationals. And, you know, so somehow we have to somehow understand how the orientation information. I'm saying this. Yeah, I'm being very sloppy there, possibly because I don't understand what's going on yet. But it should be like part of the orientation information should be telling us which components of the system we're in over the rationals. But then there should be more detailed information which tells us which components we're in over the algebraic closure of the rationals. And, you know, so the difference between those two levels is the difference between knowing the one precise specific children's drawing versus just knowing the whole Grothendieck Teichmüller orbit of that child's drawing.
I'm confused about, so you have like the children's drawing versus its Grothendieck Teichmüller class, and then you've got this, and then you've got the census information.
Yes, or the Young diagram information, yes.
Young
diagram is the census, yes, go ahead.
Yeah, versus the more detailed information where you actually have the whole child's drawing. That is, you have the whole branched cover. Are those supposed to be the same? Sorry, I said them in the opposite order from each other. Those two pairs of fine-grained information and less fine-grained information. Are those supposed to be the same thing?
Well, that's what I'm struggling to clarify. It's something like that, but some, yeah, I mean, right. That's a reasonable guess. I mean, there are a bunch of. I mean, we have this. We have several conceptual pictures that should all be equivalent to each other. You know, one conceptual picture is the actual child's drawing. Another conceptual picture is the pair of permutations. And some other conceptual picture is these zero-dimensional rational algebraic varieties that we're trying to invent. And as we invent them, we may need to have sort of brush away certain unwanted components that are just purely accidental and we don't really want them or something like that. But when we get down to the ones that we really want, there should be components corresponding to different orientations between the permutations. Something like this. Again, we need to clarify this. I mean, we have these different conceptual pictures, and then in each conceptual picture, we have various levels of coarser information versus more fine-grained information. And it's very natural to conjecture that, you know, this intermediate level of coarseness over in this conceptual picture corresponds to this intermediate coarseness, intermediately coarse level of information in this other conceptual picture. And I don't know, and there's probably a whole bunch of these conjectures that we can make, and we're trying to develop a correspondence here. And I don't have the, you know, I don't have the final clarified answer here yet, but that's what we're trying to fumble through here. That's what we're trying to, that's the deep conceptual thing that we're trying to fumble through here. And, you know, we're supposed to reinvent the Grothendieck Teichmüller action in this way. And so that's what we're trying to do here. Well, sorry, there's so many things I'm trying to say at the same time. So I'm getting, you know, I'm making it sound very disorganized because it is very disorganized. But so that means I have another thing to throw out right now, which seems like very important, but it's a little bit digressive, but I have to say it anyway. So we're fumbling our way into this conceptual picture where we're trying to get these rational algebraic varieties, and those rational algebraic varieties, just by virtue of being rational algebraic varieties, they should embody this Grothendieck-Teichmüller action of the absolute Galois group of the rationals. But so we are doing the right thing so that we're getting rewarded with an action of the absolute Galois group of the rationals. At least that's the way it looks so far. But, or in the end, we will earn this reward. But from my point of view, there's still something funny about this, because I don't see that we've committed any good deed yet that explains why the action is going to be so nice, why the Grothendieck-Teichmüller action is going to be so nice. So in particular, the rumor that I've heard, which, I mean, maybe it's obvious when you think about it from the right viewpoint. Maybe it's obvious that's going to work out this way. But at this point, at this moment, I'm still just thinking of it as a rumor that the way that the Grothendieck-Teichmüller action is going to work is that it's going to act by group automorphisms. Well, at first I was going to say group automorphisms of the free group on two generators, but maybe to be much more morally correct, I should say topological group automorphisms of the universal profinite completion of that group. Because, right, that means we're only interested in finite Children's drawings, basically, right? Because from a Tanakian viewpoint, the finite connected actions, the finite transitive actions, is exactly the continuous actions of this universal profinite completion.
Okay.
I think I'm fumbling my way through this, but I think that's the way it works. So so that means we may have, I'm vaguely imagining that this automorphism group of the universal profinite completion is, maybe it is itself a profinite group or something. I'm not even quite sure about that, but right, yeah, I'm imagining some of these automorphisms being defined level by level in the tower of profinite, the tower of finite quotients of this profinite group. So it could be, I'm imagining it could be larger than, it should include all the actual automorphisms of the free group on two generators. Those will just functorially induce automorphisms of the universal profinite completion. But I'm imagining that there may be other automorphisms that can be defined level by level. And right, so I was saying that the rumor I've heard is that somehow the absolute Galois group of the rationals will be realized in this way, that it will be perhaps some subgroup. Right, so is this now I'm very unclear because I'm using this silly non-cheating method where I try to reinvent everything myself. There's a lot of things I don't know here, whether they're actual theorems or conjectures or whatever. But I mean, I have a feeling there's probably some theorem that says that you actually do get, this process actually is faithful on the absolute Galois group of the rationals, that we're going to get the absolute Galois group of the rationals be getting realized as a subgroup, perhaps a closed subgroup of, in an appropriate sense, of the automorphism group of the universal profinite completion of the free thing on two generators.
Yeah, that matches with my vague understanding. I don't think they'd get quite so excited about it if it was just like giving you a quotient of the absolute Galois groups.
Right. I think that's going to be a theorem, but I think they're going to, there are things that at least 10 or 20 years ago or whatever were just conjectures that say that you can nicely characterize the image of this representation of the absolute Galois group. And so I'm still unclear on exactly what those conjectures say, and even more so, I'm confused about what did we do? What in the world could we possibly have done that entitled us to get this action of the absolute Galois group to be via automorphisms of this group, the automorphisms of this topological group, this profinite topological group? You see what I'm saying? I mean, we've got, right now, I mean, what's our conceptual picture? We've got a functor from the continuous actions. We have a very nice functor from the continuous actions of our profinite group, a functor from that to rational algebraic varieties, to zero-dimensional rational algebraic varieties. And that's very nicely giving us, pretty nicely giving us automatically some sort of action of the absolute Galois group. But why is that? Why can we see that action as being an action via automorphisms of this profinite group? Am I missing some obvious thing there yet, or something? I don't know. I mean, I'm leaving this as an unanswered question for now, unless you have anything you want to suggest about it. I mean, I could easily be missing something very obvious or something like that. But right, I mean, it's like I've got this functor from the continuous representations of the profinite group to rational algebraic varieties. And this functor is probably a very nice functor. It's probably like a, you know, it's probably, looked at in the right way, it's probably like an interpretation of theories in some doctrine or something like that. But how is this then giving us a homomorphism from the absolute Galois group to the automorphisms of the profinite group? I don't quite see a process that's automatically doing that yet. But maybe there is some. Yeah, go ahead.
Can you crisply say what that algebraic variety is? So we sort of worked it out. Example.
Well, that's an important thing that it's on the schedule for today, and we have more than a half an hour left, so maybe I will get to it. But let me try to give you an ultra short version of that. Well, what am I trying to say?
Yeah, I mean, I was thinking that like if there's a short description of it. So I mean, the way you stated the puzzle, it like
interrupted my sentence, but go ahead. Yes, go ahead. Go ahead.
The way you stated your puzzle,
yeah,
sort of like zipped past the stuff about branched covers of the projective
yes
line, branched to 2 points.
Yes.
And sort of the first half of the puzzle was just all about getting these zero-dimensional algebraic varieties.
Yes.
But so you have to tell me like what those varieties are like more in terms of these branched covers so that I can see the free group with two generators or its profinite completion. So I can see it in the description of this functor. And then we'll be more likely to be able to see why we'll be able to see why automorphisms of that free group are showing up.
I'm not sure I understand what you're saying. I mean, right, because we have these two permutations. That's this finite action of the. That's a finite action of the free group on two generators, or equivalently, a continuous action, a I mean, I'm just being slightly sloppy there. What am I trying? Right. I mean, I have to put in all the. If I try to, there's some annoying fine print to put in here. But yes, what?
It's maybe that just I'm not remembering how everything fits together well enough. But I don't need fine print so much as I need.
Yeah, I'm just saying. What am I trying to say? That. I mean, the children's drawing is basically, right? You can move back and forth between the children's drawing and the pair of permutations.
Yep, I can do that.
And the pair of permutations, right? If you pick a bad pair of permutations, you could get a disconnected child's drawing. So maybe we should, talk about just the good pairs of permutations. And those good pairs of permutations, those are basically right. So that basically means a transitive finite action of the free group on two generators, and a finite transitive a finite transitive action of the free group. Right, that was the only fine print I needed really, and it's a finite transitive action of the free group on two generators. That's a synonym for transitive continuous transitive action of the universal profinite completion.
Sure.
Okay. So those are three conceptual pictures we can move back and forth between very freely.
Yep.
And
yeah, I'm not, so that's not what I'm worried about, and it's not what you're.
Okay, but it sounded like you were worrying about that. I mean
no, I was not worried. No, you said
yeah,
I can't even remember what you said. You said like we've got this functor that does to give me something or other, I can't even remember what it is, and we get a zero-dimensional algebraic variety.
Yes, well, I mean, there's a couple of different functors here. Yes, go ahead.
Yeah, well, tell me what one of those functors goes from and to.
So one of them takes in equivalently either the child's drawing or the pair of permutations or whatever.
Yeah.
That's the input. And the output is this zero-dimensional algebraic variety, which, it's just this system of equations that we're grinding out. Now, the good functor is supposed to give us an irreducible system. A system that just has one component over the rationals. But so far we have one that gives us multiple components. And that's because, it doesn't depend on the orientation. If we sharpen it so that it depends on the orientation some more, we're not quite clear on how much it should depend on the orientation yet. We want to sharpen it just enough so that it depends on the orientation to some extent, just enough so that we'll get these things that are irreducible over the rationals. And I think that's what we want.
Can you restate the puzzle about how the
what puzzle?
Your other, you stated this big puzzle. How do
that big puzzle?
How do why does something give automorphisms of this?
Yeah. So by virtue of getting this right, but so right, we've got an action or homomorphism that goes from the transitive continuous representations of this transitive continuous set valued representations of this profinite group, which is the syntactic category of some sort of theory, right? It's going from there to the zero-dimensional rational algebraic varieties.
Yep.
And just from the fact of where it lands, the fact that the codomain of that functor is the rational algebraic varieties, you can extract from that an action. Because, right, I mean, the absolute, I'm saying this in a slight way, but the absolute Galois group of the rational, its whole purpose in life is to act on the solutions in solutions in extension fields of things that are defined over the rationals.
Yep.
And so we've got a thing that goes like that. But somehow we're getting allegedly we're going to interpret this action in terms of an action of the absolute Galois group of the rationals on the profinite group, on the universal profinite completion of the free group of this free group. So an action of this absolute Galois group on this profinite group.
Do we even see?
So right, I mean, it's like there's an arrow going in a completely different direction. We started with an arrow going one direction. Now it's getting a different arrow going in a different direction. Yeah.
Do we even see from this stuff you said why the absolute Galois group should be acting on the children's drawings? So just because they're giving us these,
we could sort of see it.
Doesn't that require that this map from children's drawings to these zero-dimensional varieties be nice enough so that when, just because you can act over on the set of all these
well, it's going to act on something. It's going to act on something, but I think it's going to be nice enough that it's going to act on the children's drawings. It sounds like you're just saying that it sounds like you're just saying that there's a faithful enough process that turns the children's drawings.
Yeah, that's what I was wondering about. So I mean, that's already confusing to me why that should be faithful enough. But yeah.
I think it's going to be a faithful, but again, that has to do with sharpening this thing, right? I mean, so far the process we have is not faithful. So far, it's remarkably unfaithful. But as we develop this correspondence between the orientations, between the permutations, and the components of this algebraic zero-dimensional algebraic variety, we should sharpen it to the point where it is faithful enough, and that's going to work. But that still doesn't clarify for me yet why we're getting this arrow that sort of seems to be going in this different direction. I mean, I may not have. I mean, the whole question is vague in my mind. I haven't really sharpened it yet, but I'm still trying to say more stuff here before we quit.
Okay.
So, but yeah, it's for me at this point, it's a big conceptual puzzle, but maybe just because I might be missing something obvious or something like that. So what am I trying to say here? So there's so many things to say here. I like 20 minutes left, but so I keep on repeating that we are apparently getting this zero-dimensional algebraic variety. And so far, right, it sort of seems like a little bit magic that we're getting something zero-dimensional out of this, right? We had a list of variables that were like coefficients of our Shabat polynomial, and the other variables were locations of the vertexes. Locations of the zeros and ones of this Shabat polynomial. And then you think about how many equations you can think of to write down, and just magically it turns out that, you can just think of exactly the right number of equations to write down that to balance out the number of variables, so it seems like it's going to come out to be zero-dimensional. And if look at how the trees are working, you realize that that balancing seems to happen because of the Euler characteristic of the, because it's genus 0. This tree, this polynomial example means that we're dealing with a very nice genus 0 thing with just single point at infinity. But what am I trying to say here? That this 0-dimensional algebraic variety that we're getting, it's 0-dimensional, but we can think of it as an intersection of higher dimensional varieties in a useful way. So let me see if I can show you an example of that, okay?
Okay.
So what am I trying to say? That like let me see if I can do an example here. Like, let's say we have like A, B, C, D, E, F, G, H, J, or something like that. And then A, D, F, J. And you compose these two permutations together and you get, this whole long thing, right? I chose the A, D, F, J. That's the initial letters of these little short words. And that this little cycle, when you can do this composite, it will automatically splice together the short cycles into one long cycle. We mentioned that. So it's like the composite is A, B. If I'm doing this right, if I didn't, screw it up in some way. And this corresponds to a child's drawing that looks something like what? It's got like a rooted tree, and there are 4 cycles there, so it's like A, D, F, J, or something like that, and then there's like the J1 just has its 1 all by itself, but the A1 has 3. I'm not sure I'm doing this exactly correct, but it's something like this, right? And the D1 should have just 2, and this should have 3. So it looks something like that. And what was my point of drawing this? My point of drawing this is allegedly that I'm trying to show how this this 0-dimensional algebraic variety we're getting it by, exactly the kind of intersection that generically gives something 0-dimensional. So what am I trying to say here? What's the degree of the polynomials here? The degree of the polynomials, is this like 10th degree or 9th degree or something like that? 1, 2, 3, 4, 5, 6, 7, 8, 9. So then these are 9th degree polynomials. So there's like a 10-dimensional vector space of 9th degree polynomials. And in that 10-dimensional vector space, we're going to have certain algebraic varieties. We're going to have 2 of them, one for the green constraints and one for the red constraints. And we're going to intersect those together, and that's going to be the conjunction of those green constraints and those red constraints. And that's going to give us the 0-dimensional thing here. So let's just try and figure it out numerologically here. So what am I trying to say? That so the red constraints is going to give us what? It looks like 3 here, right? So 3 here, 2 here, 3 here, and 1 here. Is that working out? What am I trying to say? Now maybe it's 1 less than that. Is that right? Let's see. How is that working out? It's the number of edges. What am I trying to say?
It's the number of edges, I think. Yeah. So it vanishes.
Okay, but I didn't say that correct. I always make this mistake. Let me see if I can phrase what I'm trying to say here. I'm trying to say, this is what I'm trying to say. There's a constraint on 9th degree polynomials, and the constraint, there's a green constraint on 9th degree polynomials, and there's a red constraint on 9th degree polynomials. And we want to consider the conjunction of these two constraints. But I haven't successfully articulated what the green constraint is that makes it different from the red. So the green constraint is all about the zeros of the polynomial.
Mhm.
The red constraint is all about the ones of the polynomial. So the
Yeah.
green constraint says, don't tell me, let me think about that. The green constraint says that the zeros are all lumped together in the way of the Young diagram. You know, this Young diagram that I guess looks like it's got 2 3s, and then a 2, and then a 1. Right, so there's a subvariety of the 9th degree polynomials consisting of those polynomials which have repeated roots according to this pattern.
Where did that thing come from? What is it? What's 4?
3 3 2 1. 3 3 2 1. That was supposed to be a Young diagram.
It seems more like the red stuff to me.
I wasn't thinking very carefully. Maybe that's the red. Okay, fair enough. I drew it in green. I'm not sure even I was trying to say that that was, did I really say that that was the green one?
Yeah, you said it a bunch of times and you drew it in green.
Okay, then it's the red one.
Okay, I thought I was getting a rare condition of red-green switch, which is like even more rare than red-green color blindness. Okay.
I'm not even sure that there isn't something like that going on here, but I'm not going to worry about it.
Okay,
so
but yeah, there is such a thing. I mean, now I get it. Yeah, now so
yes.
basically you're just sort of saying that the zeros, or maybe it's the ones, are of, that there are four of them and they're of specified order.
Yes, so it sounds like you're saying that this is,
You know what?
it sounds like you're saying this is codimension 6 constraint or something. Is that right? Because it's a 4-dimensional subvariety. What am I saying? I mean,
I don't know what. Sorry, I didn't get where those numbers were coming from.
Well, I'm describing a certain subvariety here, and I'm trying to figure out the dimension of this subvariety. Maybe it's a 5-dimensional subvariety, because, right? I mean, right, by having the repeated roots in this way, I'm getting something that in effect acts not like a 9th degree polynomial, but acts like a 4th degree polynomial. So, right, so instead of being this 10-dimensional ambient variety, it's this, right, there's a 5-dimensional. Is this really gonna work out like this? Let's see, how am I gonna? I'm having trouble getting this to balance out in this tape. Let's see, what am I trying to say? So, see, the problem is this one seems like it's just gonna be 1 dimension. Am I saying that right? It's gonna be, you know, the polynomials.
Sorry, which one? The one that has the 1 up there?
Oh, yeah, yes, I'm sorry. So I forgot. So yeah, this one has 4 orbits, but this one has, don't tell me, it has a whole bunch of singleton orbits that I forgot to count, right? So this one, right, this has like 4 at the top, and then it's got something down here, and so it's like 5 of them down here. I think that's what this one is. You know, this Young diagram is this one up here, and this one up here, because all those singleton orbits that I neglected to write in the cycle notation,
right,
are just these little things down here.
Yeah.
So this actually, this looks like 4. And this looks like 1, 2, 3, 4, 5, 6. And I think that's right. Is that working? Is that working? So I'm saying that there's a 4-dimensional variety and there's a 6-dimensional variety, and I'm claiming they should intersect in a 0-dimensional variety. I think that's what's going on here. So right there.
Confused about the numbers, but I get the vague general.
Yeah, so there's this subvariety of there's this subvariety of ninth degree polynomials that have their zeros repeated according to this pattern at top. And then there's this other subvariety of ninth degree polynomials that have their ones repeated according to the pattern at bottom. And you intersect those two subvarieties and you get this zero-dimensional subvariety.
This has nothing to do with specifying the locations of any of those zeros and ones, just
that's right. It has nothing to do with that. But that information, though that when you intersect those two, that somehow is going to constrain those locations.
How come when we were doing the examples, we just went ahead and specified that one of the zeros happened at 0, and one of the
there was just some gauge freedom we were exploiting.
But here it seems like you don't have any such gauge freedom. Here it sounds like you're saying that like you just specify the multiplicity of all the zeros and ones, and that just like
well, maybe that, okay,
maybe that's the mistake.
Yeah. I mean, right.
But there's got to be the gauge freedom.
You've pointed out a little glitch there. But it's going to work out somehow. Somehow, when you do this the right way, it's all going to.
Okay, well, there should be a little, yeah. So anyway, so somehow your count here should be a little bit off, and then that should somehow.
That's right. That's right.
Okay.
That's right. So
that's, yeah, anyway, it is sort of amazing that it works. Yeah, if it works, yeah.
Yeah. And again, we're trying to sharpen this functor so that we're going to get something that's irreducible over the rationals. And we should be able to, somehow that should be some information about the orientation. So, by the way, I'm just throwing out random silly ideas here, as usual. And in the actual child's drawing picture, there's an interesting intermediately coarse level of information about the orientation that you can consider. Which is, am I saying this right? I think this is finer than just knowing the two Young diagrams. I think it contains some information about the orientation, but it contains incomplete information about the orientation. That's why I say it's an intermediately coarse level. So a children's drawing in this tree example, it particularly contains some planar information, which is more information than just the non-planar tree. Right? There's an underlying non-planar tree of our child's drawing.
Yeah. Wow.
And I know that this, planar versus non-planar information shows up in certain places when people create interesting examples. So that's just one of the silly ideas that I have. Maybe the information in the planar, the limited amount of information that you just get in the planar tree. I mean, does the planar tree even contain any more information than the pair of Young diagrams? I think it does, but it's obviously not the complete information, because you can easily draw two child's drawings that are identical as non-planar graphs.
Sure.
And
yeah, I mean, you could just like take one of those branches of your tree and just plop it over somewhere else. And
that's right. Just rearrange the clockwise order of these of this cycle of that's right. So this isn't that bad. I have like 5 minutes left to try to say something. I want to say something very well. I'm hoping you're getting a sense of what we're trying to do here. I mean, obviously there's way more elegant and finished and complete ways of doing whatever it is what we're trying to do here. And eventually I will try to read, all this stuff about Shabat polynomials and everything and find out how people actually do it. But, I'm having so much fun here trying to reinvent it that I'm still not at the point yet where I'm ready to really look at the textbooks. But in my remaining 5 minutes, I just want to throw out a couple of more vague, wild guesses about these intermediate levels of information that might correspond to, interestingly intermediate levels of information about the orientation that correspond in this particular conceptual picture to just some level of information about the child's drawing in this conceptual picture, some level of information about the orientation between permutations. Well, so let me do this, okay? So you started out saying something that you said something like, well, I can see that there's something double coset-y going on. And you're absolutely right. But these double cosets are double cosets between permutations. And we represent, like the information in the single permutation is basically just it's the Young diagram indicating the cycle structure. But this also reminds us, right? This reminds us of a sort of different double coset classification problem. The most famous one of all, which is sort of the Bruja classification. And that's also about things that are sort of represented one at a time by a Young diagram. But it's not permutations, it's something different, right? It's just flags or partial flags or permutations as sort of, field with one element, degenerate special case of partial flags, just partitions. So, right, so one of the things we're saying here is that a permutation, the information in a permutation, even just in a single permutation, has a coarsened level, which is just its cycle partition.
I see. You're not losing anything when you consider a single one that is up to isomorphism.
That's right.
But when you
That's
consider
right.
two, then you're losing more. Yeah.
That's right. That's right. So
have you ever thought about? So there's
have I ever thought about the combinatorial classification?
Yeah. The classification of bipartitions and bipermutations. I mean, we're talking about bipermutations all the time here, but
I've sort of thought about it a little bit before. Like, I mean, the particular context I remember thinking about it, I can't remember. It's so annoying. I can't remember exactly why I was doing this and exactly the results I got. I was using Mathematica a lot to do calculations, but I was doing things like, it was the usual sort of Hecke operator game that I was playing that led me into the double coset thing. But I was doing this I was taking I was treating consciously classes of permutations. A consciously class in n bang. I was treating that as a permutation representation of n bang. And I wanted to, turn that, I wanted to extract the irreducibles. So that's an right? That constant class is an indecomposable set value representation. But I wanted to linearize it, get a vector space representation and take the irrep content of that. And that's, of course, a double coset game, a Hecke operator game. And so I remember doing a lot of that, but I can't, this was like a couple of years ago. I don't remember, if I dig through my notes, dig through my programs, I may be able to get something, learn something from that. But anyway, I'm now facing that situation again, but in this context of learning about children's drawings. And so, I've got 2 or 3 minutes left here. I don't have that much to say, but I'm just trying to say that.
Okay. By the way, new order,
I have a little bit to say, but go ahead. Yeah.
No. But the new regime is that in 2 minutes or whatever it is, Todd Trimble is gonna show up for my next conversation. So
yes.
you'll
Sure.
create some kind of
Sure,
see
that's all the more reason for me to let me try to finish my sentence here. If I can remember what the sentence was to finish.
No, but anyway, I'm very nervous. So like screw up the whole video if I could, if Todd shows up. But anyway, okay, go on.
Well, so I'm just saying that this extracting the cycle partition from the permutation, that's a coarsening process.
Yeah.
And the silly wild guess I'm stating here, I don't even believe any of these wild guesses, but I'm saying that in this conceptual picture, that's an interesting coarse level of classification. So it's interesting to consider how that corresponds to these other coarse levels of classification that we have in some of these other conceptual pictures. So I'll just leave it there for now. But I hope you can see that there's lots of exciting stuff going on here. It's really fun to try to figure this out. I'm hoping you can see how fun it is. That's the main thing to learn here.
Yeah, even though we were like trying to solve a quintic equation and got completely stuck, but yeah. But yeah,
that's part of the fun. That's part of the
fun. Okay, that counts as fun, I guess. Yeah, no, it's fun.
all sorts of things I'm forgetting to say here. But
well, that's good because we got to stop.
Sure. All right. So if I leave before Todd shows up, just say hi to him for me.
Sure. Yeah.
And all right. Okay. I'll see you. Bye.
Okay. Yeah. Bye.
Okay.